a couple of things about this, and then we'll bring it all together. One interesting fact is that even though we write F minus here over on the right, fluoride, and it's in toothpaste, the sodium fluoride, working with fluoride sources can be incredibly dangerous because it is a deadly reagent if it interacts with your bones in particular and decalcifies your bone. So we'd like to have a gentle way of introducing fluoride. And so common, I'll put it down here, common fluoride source is having a nitrogen with 4 butyl groups. So it's a positive charge, and it's a salt, and it's F minus. And so this is tetrabutyl ammonium fluoride, or TBAF for short. So you might just see the letters TBAF written. This is a nice way of introducing fluoride. You could use something like hydrofluoric acid, HF, but this is the one that's deadly. And so we're not going to use that. Could use it on paper. It used to be used in peptide chemistry quite a bit, actually, for deep protection. And I've actually never worked with it. We use something else in place of it. One little other side point, too, that's kind of interesting, perhaps, is that fluoride, something like HF, actually eats right through glass. And this is because glass is right, silicon dioxide. Since fluoride loves silicon so much, if you try to do a reaction in a glass flask or beaker with HF, it's just going to eat right through it and destroy it. So you actually have to do everything in plastic. In some ways, it seems kind of strange. You're working with this really deadly chemical, but everything is in plastic. So TBAF here supplies the fluoride, but in a much gentler way. One last one, if you're interested in this, is you might use something like this pyridine species that's coordinated to fluoride. And this usually just abbreviated as HF pyridine. This one comes in plastic bottles. It's a liquid. I remember using this a little bit as a graduate student. We would actually run some of the reactions in glass, which we probably shouldn't have done, in a very dilute solution, but it would etch the glass. You would see where it came at the top. So now I'm going to address a couple questions in an overall point here. So I was asked to scroll up a little bit. And down. Oh, sorry, yeah, I think I didn't have it all the way down there. Yes, all right, yeah, no problem. Yes, and it's the glass, you cannot use glass because it's silicon based, exactly. So that's why you use plastic for it. Fortunately now, in terms of peptide chemistry, at least, there are substitutes for this HF. Those types of things, it's not like this is going to be on the exam, but hopefully it makes it a little bit more interesting, just as we're writing all these letters and numbers, so trying to think about these a little bit more as chemical reagents. So now let's summarize and bring in a couple of other aspects. There was a great question about, in the final product, is the more substituted carbon a chiral center? And the answer is yes. And so this Grignard green reaction here makes a chiral center at this particular spot here. So you are going to end up with a mixture of stereoisomers. I'm intentionally ignoring it here. And when we have quizzes or exams, if stereochemistry is important, I will make sure to state, please show both stereoisomers of form, or I can state that you can ignore stereochemistry. But you're exactly right. So in this particular case, we do make a chiral center. However, I'm not showing it here just to simplify this. Now, along those lines, going all the way back to the beginning, well, it's not the beginning, it's here. This other carbon on the left side here is a chiral center. And if I may scroll up a little bit, that's okay. Our starting material, notice here in the left, had that chiral carbon with the alcohol, and it was the R stereoisomer. So oxygen is 1, this group is 2 because it has the tiebreaker with the carbonyl. Methyl is 3. I put hydrogen in the back as 4 intentionally because it's easier than to know what it is. You go around clockwise, and so this is R. Then if we go all the way down to the final product here in the bottom center, it's also still in R configuration. So this siloprotecting group did not change the stereochemistry. So that's very important, because really you want this protecting group to serve its purpose during the reaction of interest, and then get rid of it without affecting anything else. So overall, then, I think I can't make this much messier. Our three-step process. We have here, we protect. So we introduce our what happens to be a siloprotecting group here. This was our reaction, we call it our reaction of interest. The key reaction, which in this case happens to be a Grignard reaction. And then over here, we didn't save enough space. How about write it sideways? Deprotect. So those are the things now to be thinking about when we're carrying out synthesis. A lot of times, if we have incompatible functional groups, or functional groups are incompatible with the reaction that we want to pursue, we need to introduce protecting groups, for example. And as mentioned, this is only one of the many sorts of protecting groups for alcohols, and there's going to be protecting groups for all sorts of other functional groups. But this is what we're going to use to introduce this idea of a protecting group. All right. How about any additional comments, questions, concerns, criticisms? Break time? Okay. Can we just do it for 5 minutes this time, if that's okay with everyone, since we started a little bit